Thank you all for coming. The title of my paper is Mastering Chess and Shogi by Self-Play with a General Reinforcement Learning. So what does that mean? A group of researchers at a company called DeepMind built this algorithm called AlphaZero. And what AlphaZero does is it's a single algorithm that is able to achieve superhuman levels of play in multiple different board games. And it achieves this entirely through self-play. And the algorithm is only aware of the rules of the game. So it's not given any expert move databases or opening books. The only information it has about each of these games are the rules. And the three games it played are chess, which I'm sure you're all familiar with, and then shogi and go, which are two Asian variants of chess, which are slightly more complicated. So the backbone of this algorithm is something called Monte Carlo tree search. And there are 4 steps to each iteration of a Monte Carlo tree search: selection, expansion, evaluation, and update. And I'll get to more on those later. But essentially, it's able to focus on the most promising moves and only dedicate computing power towards evaluating those promising moves. And it's aided in the search by a deep neural network. And what that is basically a mathematical model that is used to approximate very complex functions. At a high level, how this works is it takes as an input on the screen a chess position, and then it outputs a scalar value between -1 and 1. And that value, the value, if it's closer to 1, would represent a more favorable board position. And then an output closer to -1 would indicate something that is likely to lead to a loss. So I'll take you through how this actually works. At the top there is a node, and that node represents just a board position in any of the 3 games. And as I said before, there are 4 different states to each round of simulation. So first we select, since there's only 1 node, we of course select the first node. And then we call expansion, and we add in all of the possible legal moves from that original board position. For simplicity's sake, there are only 3 here, but in something like chess or shogi, that number can be upwards of 15 or 20, so this tree will rapidly expand. Next, we call evaluate on one of the child nodes, and as I said before, we pass the board position into the neural network, and that returns us a value. We then call update and store that value in the node, and we also keep track of how many times we visited that node. So then we repeat evaluate and update on the remaining 2 nodes, and then we're left with this tree. So now that we finished 1 round, we again have to call selection. But now that there's more than 1 node, the selection process is a bit more complicated. And basically, the selection process seeks to balance 2 parameters. First, we want to explore nodes that are very promising. We obviously want to investigate nodes that have a higher value because they're the ones that are likely to lead to a win. But we also want to explore nodes that we haven't really investigated yet. At a first glance, a node might have a low value, but if we investigate it further, there might be 1 or 2 lines of play that are actually very promising and that we wouldn't want to miss. So if we assign arbitrary values to these nodes, then we would of course select the left one because it has the highest value. Then the process is the same as before. We call expand again and add in all of the legal moves from that board position. We then call evaluate again and update. And update not only updates the child node, but it also updates the parent node, incrementing the amount of times we visited it and also factoring in the value into the parent node's value. We then do evaluate and update the remaining nodes. And we repeat this process many times until we reach a tree that may look something like this, where we visited all these nodes many times, and all the nodes have long branches branching off from all of them. So in this case, if we originally passed that word position into the algorithm, then the algorithm would choose the leftmost move to play because it had the highest value. So initially, the parameters of the neural network are completely randomized, so its predictions are very bad and just random. But as it plays games against itself, selecting moves via the process I just explained, it's able to use those game results and update the structure of the neural network so that its predictions become more and more accurate, and it predicts its predictions become more closely to how the games actually turned out when it played against itself. So then the researchers wanted to test, of course, how good it is. So they organized 100 game matches against top engines in each of the respective games. Stockfish in chess, Elmo in shogi, and AlphaGo Zero, which is just a previous iteration of the AlphaZero program in Go. So to put those results in perspective and demonstrate the strength of an engine like Stockfish, this is Magnus Carlsen, who's the current world chess champion. And in this picture, he's playing against 10 international masters completely blindfolded, and he beats all of them. And he has an ELO rating of 2834, which is just an objective measure of a chess player's skill. And then there's Stockfish, which is AlphaZero's opponent in this 100-game match in chess. And it has an estimated ELO of around 3,300, almost 500 points higher than that of Magnus Carlsen. And what does that mean? That means if Stockfish were to play 100 games against Magnus Carlsen, Stockfish would be expected to win at least 95 of those games. So Stockfish is a very strong engine, much stronger than any human player. But then when AlphaZero plays Stockfish in chess, it didn't lose a single game against Stockfish. It won 28 games and drew the remaining 72. It performed similarly well against Elmo in shogi, winning most of the games and only losing and drawing a couple. And then it performed, marginally better than a 50-50 win-loss ratio against AlphaGo Zero, which is just a previous iteration of itself. And something that's interesting is that AlphaZero is evaluating significantly less positions per second than Stockfish. As you can see, in chess, it evaluates only 80,000 positions per second, whereas Stockfish evaluates 70 million per second. The reason this number is significantly so much lower is because its neural network guided search allows it to focus only on the most promising moves and the most promising lines of play, and completely ignore the ones that are bad and not dedicate any computing power towards those. So with that, I conclude my presentation. I'd like to thank the Journal Club team for helping me prepare and refine my presentation. Mr. Burkhart for teaching me about ComSci and how all this stuff works. My family for supporting me, and all of you for listening. Any questions? Yeah.
As someone who has light knowledge of machine learning, what do you think the big picture reason for training something on games is? Do you think it's to further develop neural networks, or is it just kind of a fun way to show the strength of these programs? What do you think?
I think it's definitely sort of a proof of concept type thing. It shows that these algorithms are able to surpass human knowledge and human ability, by such great margins that, and that was something that was, 20 years ago previously thought to be impossible. And, I think it sort of pushes the boundary of machine learning and will, help it expand into the other aspects of our lives.
Cool, thank you.
Got it? All right, thank you, Billy.